Okay, so we're going to take a look at potential energy functions, specifically in graph form. Now, potential energy functions can get a little confusing, but basically what we're doing is it's a way of modeling how much energy is being stored in a potential energy associated with a conservative force. So one of the best ones to look at and to think about for these is gravity. Now, we know that we end up with some potential energy stored in gravity. I usually mark it as PE sub g when we're close to the surface of the Earth. The AP exam and the more broader usage might refer to it as U, a capital U. These are both saying the same thing, they're just different notations. This one is the standard notation, but I find that it's a little confusing when you're first learning it, so I like to use PE for potential energy. Now, what we found is many times you have, for a system that's undergoing motion with conserved energy, in other words, only has conservative forces acting on it, you'll find that you have kinetic energy and potential energy kind of working, I don't want to say against each other. What they're actually doing is, as you lose one, you gain another. So for instance, if I take an object, it has some gravitational potential energy, being some height up. It's got a lot of potential energy right now, and I let go of it, and it would begin to fall, releasing that potential energy and putting it into kinetic energy. By the same token, I can take something, give it a lot of kinetic energy, and toss it up in the air, and as it goes higher, it gains gravitational potential energy by losing kinetic energy, and it slows down, and stops. Then it comes back down, because that's how gravity works. Now, one of the things that I'll point out is how much energy I give it initially will affect how far it can go in this gravitational potential energy. So for instance, if I throw it just a little bit, it'll go up just a little ways and then stop and come back down. If I give it a lot of kinetic energy, it can go flying very far up. And that's the idea behind these potential energy curves. Now, one of the classic ones that we deal with, although it's not the only way to look at it, you might end up with a graph that looks something like this, where our potential energy curve might look like this. In fact, that's the example problem that I want us to take a look at. It's from an old APB exam. But first I'd like to give you an idea of what it means. So normally what you've got is some position, and so we could say that this is x equals 0. And let's say that this is some position here that we will call, let's say 4. Let's go 1, 2, 3. 1, 2, 3. And then we've got 5, 6, 7. Then maybe 8 way out over here. Now we've got something that basically what this means is, if this is our potential energy curve, it tells us how much energy, potential energy, something has at a given point. So for instance, let's say that, so this is a position of 4 meters. Let's say that this has an energy of, I don't know, 10 joules, and then maybe 20 joules, and then 30 joules, and then way up here off of our chart is 40 joules. I guess I could continue drawing this. Usually these potential energy functions will keep going for quite a ways, farther than the graph. Basically what this says is, if I have an object and I put it right here at 4, at position 4, it has 0 joules of potential energy. That's what this graph is telling you. Basically, if you have something at a given position, how much energy it has. At 3, I'd have to read off of here, but maybe 2 joules. At 2, we're getting closer to maybe 8 joules. And at a position of 1, if I have to drag it all the way over here, I'm almost up to 20 joules. If I get down to a position of 1/2, I might be up at 30 joules. And so we've got something where, for some reason, as I move farther away, it requires more energy. And I'm going to give you an example. If you're having a hard time imagining what would result in this, there's actually a really great thing to help visualize it. But the point on this is as I move things to different points, this tells me how much potential energy is at that given point. All right, so let's imagine where this particular graph might come from, and for that, I'm going to rely on one of my favorite sources, the University of Colorado, if I'm not mistaken, the PhET simulations that they have. Now, I've stepped away back over here, but hopefully you're still able to see this just fine. We have a skateboarder, and we've got a U-shaped pipe, whatever skateboarding pipe. So what I can do is I can actually take the person, I put them If I put them at the very bottom, they have pretty much no energy and they just kind of wiggle back and forth. However, if I put them up here, imagine the graph we just looked at. Over here would have some energy associated with it. Maybe this is 20 joules. I let go of them. That's how much potential energy they have, and you can see that it goes into kinetic energy and then back and forth into potential energy. In fact, I can actually show this as a bar graph over here, and we can see that we have some total energy, and it goes back and forth from kinetic to potential as this skateboarder basically swings back and forth. And this is gravity, a gravitational potential energy. And that's a conservative force, so it's easy to work with for these graphs. Now, not all the graphs are going to be gravitational, but it's usually just fine to think about them as though it's this, someone kind of skateboarding back and forth. Now, let's see. What I can do is, oops, if I pick this person up, I set them down, you can see our total energy is 0, nothing's happening. If I put them over here, we end up with less total energy, and it's constantly going back and forth between the kinetic and the potential. So this is the basic idea. Over here, I would have some potential energy due to gravity. I don't know, 30 joules. And that's also my total energy over there on the right on the bar graph. And that's my total energy, and it goes back and forth. As we lose potential energy, we gain kinetic energy. And so this is a great way to think about it. All right. One of the things that we could include in here is the same thing, except now it has friction. And we could have our total energy. However, over time, because of friction, we lose more and more of that energy to thermal energy, losing it to the work done by friction, and we slow down. This is a better representation of real life. Now, we're not dealing, at least in most of these problems, with something that has a dissipative force, a non-conservative force like friction, but there are ways that you could imagine that. The easiest one to work with is this, where we have a fully conservative setup. All right, great, because that is going to bring us back to what we were working with over here. All right, give me just a moment, I'm going to check my recording. I apologize about that, but here we go. So now you've got a way of visualizing this. It's basically the skateboarder going back and forth. And if they start off down here at 4, they have 0 potential energy. If they're not moving down there, then they have 0 total energy, and they just sit there. It's kind of boring. If, however, I put them up here, maybe at 6, and they're at 15 joules, and I let go of them, well, under the right circumstances, just like with a skateboarder, the thing can start sliding down this way, and it will speed up, it will gain kinetic energy as it loses potential energy. And so it'll go all the way up here until all of its energy, 15, is back in potential energy, and it has no more energy, so it stops there, 0 kinetic, and at that point, it can start going back and forth. So if my total energy were 15, I go back and forth with all of the points that are at 15 or below. I can't get up to 20 joules because I don't have that much energy. If, however, I started off at 30 joules, then I can go all the way up to 30 on the other side as it goes back and forth, but I can't go above the 30 joules. Great. So let's take a look at our sample problem. Ooh, where did I set it? Ah, here it is. So here's our graph. This one comes from an old AP exam. Hopefully you're able to see it pretty clearly. Sometimes the graphics don't copy as well, and I don't know how well this camera is picking up all the detail. But we've got the graph that you can see here on gridded paper, and they've got it centered at x equals 0. We've got 2, 4, 6, 8 centimeters, and -2, -4, -6 centimeters. They've also got 0.1 joules, 0.2, 3, 4, 5, 6 joules. All right. Question A, part A, says, what is the, let me give you some background. They tell us that a 3 kilogram object, so an object with a mass of 3.0 kilograms, is subject to a restoring force, F, is undergoing simple harmonic motion. You can ignore that for now. It does better describe what's going on here, but in short, this thing is being subject to what we would call a conservative force, and therefore it has a potential energy associated with it, and this is the graph of that potential energy. In fact, it says the potential energy U of the object as a function of the distance from its equilibrium point, the center point for simple harmonic motion, is shown above. This particular object has a total energy, E total, of 0.4 joules. Now, in reality, the way that they've set this up, this might be a mass on the spring that's going back and forth, but you don't have to worry about that in this circumstance, because again, with any of these graphs, you can actually imagine it a lot like the skateboarder. They've told us that our total energy is 0.4 joules, and that this thing has a mass of 3 kilograms. All right, it says A, what is the object's potential energy when its displacement is plus 4 centimeters from the equilibrium position? Well, this is 0, 2, and here's 4. On this curve, where it's at on the skate park is, I don't know, right about there. So that's between 0 and 0.1. My estimate is about 0.05 joules. We bring up the solutions on this, but basically this is just asking us what the potential energy is right there. Well, that's what this graph is showing us, how much potential energy we have. And when I'm at when I'm at 4 centimeters, I'd be about here, and that's about halfway between 0 and 0.1, so I end up with 0.05 joules. That's what the graph tells me. Great. That was part A. Part B. What is the farthest the object moves on the x-axis in the positive direction? Explain your reasoning. In other words, they're asking, how far can it go this way? Well, let's see. We need 0.05 joules of potential energy to be here. Well, we've got more than that. We could keep going up. Up here, we need 0.2 joules of energy. How much energy do we have total? It's being split between our kinetic energy and our potential energy that we see here. Remember, with the skateboarder, they'll go as far as they can until they run out of energy. So if they tell us that our total energy is 0.4, the farthest we're going to get is when all of our energy is in the potential energy, which means here's 0.4. The farthest that we would get is 10 centimeters. And the reason behind that is because at that point, we run out of energy. All of our energy is in the potential energy, and therefore we have no more kinetic energy, so we can't continue moving. Because to move, we need kinetic energy. All right, we'll keep going. C, part C. Stop that board. C. Determine the object's kinetic energy when its displacement is -7 centimeters. Well, that's getting a little more interesting. 0, -2, -4, -6. They're saying that our displacement is -7, which means we're right about here, which means how much energy is in our potential energy? Well, 0.2. So at x equals -7 centimeters, our potential energy is equal to 0.2 joules. Okay? So how much energy do we have in kinetic energy? Well, our total energy is 0.4, and 0.2 is in potential energy. That leaves 0.2 joules to be equal to our kinetic energy, which means 0.2 joules is equal to 1/2 mv squared. And that means that 0.2 joules equals 1/2 3 kilograms times v squared. Hopefully you can see where we're going here. I need to multiply this by 2. So I multiply by, let's see, 2/3, technically divided by kilogram. 2 divided by 3 kilograms. And we end up with the following. I guess I should grab my calculator. All right. So we go with 2 times 0.2, and then I divide that by 3, and we end up with 0.133, technically the 3's are repeating, joule divided by kilogram is meters squared per second squared equals v squared. So the last thing I need to do is I need to take the square root, and we end up with that our velocity, the speed at that point, I should say, is 0.365 meters per second. Great. Okay, well, we're almost done. At least with the part that we're going to take a look at. We're going to skip over the very last part, which is E, which is a projectile motion problem. Actually, no, I think it skipped over something. Yeah, no, we're not going to look at part E. Part D, however. What is the object's speed at x equals 0? Well, when the object is right here, how much potential energy do we have? Well, that's at the bottom of my potential energy, so that means that we have 0 potential energy. Potential energy equals 0 joules at x equals 0 centimeters. So that means how much do I have in my kinetic energy? Well, that means I've got 0.4 joules. And they're asking what the speed is, so we know that our kinetic energy is going to be equal to 1/2 mv squared, so that'll be equal to 0.4 joules. And we do basically what we did just a moment ago. We've got 1/2 times 3 kilograms times v squared equals 0.4 joules. Okay, so let's see what we get. I'll take 0.4 times 2 divided by 3. And then I take the square root of that, and we end up with, our speed should come up to 0.516 meters per second. In other words, about 52 centimeters per second. In short, this is how you work with it. Mainly what you're working with is, we've got just the potential energy here, and it's trading off energy with our kinetic energy. Now, there are some more advanced ways to work with some of these. Not all of them look exactly like the skateboarder. In fact, sometimes you'll end up with non-symmetric ones, and that's entirely realistic. In fact, there are some that I can tell you about. If you look at gravity in our solar system, you'll end up with a potential energy function that looks a little more like this. Now, I'm not going to go into all the details that cause it, but the graphs are still read the same way. You've got energies over here, maybe 10 joules, 20 joules, 30 joules, and down here, this is where it gets extra weird, you can have negative values. Now that doesn't mean that you're in debt any energy, it just means that you're below your reference point. Now this is something that we usually talk about a bit in class, but when it comes to potential energies, we could set our y equals 0 anywhere. So for instance, I could say that this is about 2 meters off the ground, and I could set ground as y equals 0 and say that this has a height of 2 meters, and I could solve for the potential energy. Or I could say that it has a height of, let's say I make the ceiling y equals 0. Sounds strange, but you can do it. This would be about -1 meter. When I plug that into our mass times our acceleration due to gravity times our height, well, if our height is -1 meter, meaning it is 1 meter below where I set my 0, then I do end up with a negative. It doesn't mean that I have no energy. I can still drop this. But it just means that it goes from -1 down to -2 down to -3. It still loses energy, it just ends up numerically less than 0. So that's where it gets a little confusing if you're not used to it. Potential energies are always taken with respect to a point. Now, I mentioned that in class because it's not like if we were teaching this in Denver, they have to say, oh, well, y equals 0 is a mile or 2 beneath us. So when we're here, standing here on the ground, we have to say y equals 250 meters or something like that. That's not 2 miles, but still, you get my point. You can set y equals 0 wherever you'd like. I could put it on the second floor and say, hey, y equals 0 there, as opposed to down here on the first floor. Long story short on this is a much more realistic representation of many potential energy functions that you might work with. In fact, if you look at the energies associated with chemical bonds, they look a lot like this too. And where those bonds are stable are when you have the atoms and molecules down in what we call a well. In other words, basically the half-pipe shape that you've got. And if you give them enough energy, they can go higher and higher and higher. And if you give them enough energy, they can actually break apart, and that's when you break the bond. Or, in the solar system, you give something enough energy, and it's moving fast enough that it can fly off into deep space and never come back. This is how you work with these. And we've got a trade-off between whatever's in our potential energy and our kinetic energy. And a key thing that you want to be wary of, as hopefully you have seen, is our total energy, because that tells you how far you can get. This object can't get farther than 10 centimeters, because that's when all of its energy is in the potential energy. All right.